Hello everyone, my name is Andreas Orthey. I'm a postdoc at the Max Planck Institute for Intelligent Systems. And today I want to present you our paper Visualizing Local Minima in Multi-Robot Motion Planning, Multilevel Morse Theory, which is a publication at the workshop on the algorithmic foundations of robotics. This is joint work with Marc Toussaint, who is heading the Intelligent Systems Lab at the Technical University of Berlin. And as the title already suggests, the topic is multi-robot motion planning. Our goal is visualizing local minima, and how do we do it? We do it with something which we call multilevel. A bit of motivation. Multi-robot planning problems often have local minima. Examples are where robots can go left or right around an obstacle, or can go before or after another. And with a local minimum, we mean a locally optimal solution path, or a bit more formal, a path which is invariant under optimization of a cost function. So if you take your favorite trajectory optimization method and you optimize a path and you can't optimize it further, then you are at a local. And our goal today is to enumerate, organize, visualize local. And you might ask, okay, but why would you do that? There are actually many reasons for that. One is, of course, that we want to increase our conceptual understanding about a problem, which is very related to this whole idea of topological complexity of algorithms. There's a nice paper by Smale 7. You can also use that to extract symbolic representations, something like going left or going right. You can use it to analyze convergence of trajectory optimizers. You can interact with the algorithm, and you can do that even non-expert. And of course you can have high-level options, basically contingencies or backup plans, and you can use it for rapid replanning, which is very related to the whole elastic roadmaps idea by Young and Oliver Brock. And our contributions are a new algorithm, which we call the Multi-Robot Motion Explorer. This algorithm visualizes local minima in multi-robot motion planning problems, and it does so by first computing a sparse graph over multi-level abstractions. Second, it uses a depth-first search and optimization to extract local minima. And finally, to visualize local minima using a local minima. And we finally evaluate this algorithm on 6 scenarios with multiple robots of up to 20 degrees in the joint state space. Just some notations. We will always talk about having M robots, and each robot has its own state space, and the state space is called a component state space. And I will also talk about joint state spaces, which is just a cleaning product of the component state space. And before I start, just a bit of related work. To visualize local minima, we need basically 2 things. We need a good representation of our state space, and second, we need a method to extract local minima from this representation. And if we talk about state space representations, we first need to talk about multi-robot motion planning in general. I would say we can categorize this problem into 2 sub-problems. Either we have a homogeneous planning problem where all robots are equivalent, or we have a non-homogeneous planning problem where they are not equivalent. For the case of homogeneous planning, we have a nice reduction to a problem which is called pebbles on a graph. So instead of having all the robots as one point in the joint state space, we have all the robots as multiple points in a single component state space. And this has been basically first defined by Kornhauser in 1984. And there are a lot of different nice algorithms to solve that. For example, push and swap by Luna or linear integer programming. And the cool thing is that you can actually use that approach to coordinate large drone teams. There's a nice paper by Wolfgang König and transactions of robotics, which I can really recommend to you. And if all the robots are not equivalent, we need to resort to non-homogeneous planning. The core idea here is that we have one representation per component space, and we need to somehow combine those representations into a joint graph or joint representation. I would say there are two big approaches. One is path coordination, which means roughly that for each component space, for each robot individually, you compute one path and then you try to combine them by finding one path in the joint state space. The other approach is that you compute graphs in each component space. Then you define an implicit joint graph in your complete state space, and you try to somehow efficiently search over this implicit graph. There are a lot of algorithms out there. I want to highlight 3 of them, which I really liked. For example, M star by Wagner, discrete RT by Solovay, or the optimal version by Schoen. And our work really builds upon all those works. We also use non-homogeneous planning, use multiple levels of abstractions on top of that. And one big thing of how we differ is, of course, that all those works, they compute one solution path, while we are interested in having multiple solutions. And once we have a representation of the state space, we need to somehow extract paths and group them. And the standard approach there is topological grouping by homotopy. So basically you say, okay, 2 paths are equivalent if we transform them into each other. The standard literature on that in mathematics is, of course, Munkres or Faber. And I wanted to highlight here 2 people, Florian Pokorny and Bhattacharya, who have extensively published about this topic. And in multi-robot planning, you can also use an approach which I would call a braid pattern grouping, where you basically group paths based on how many pairwise crossings of robots you observe. There's a nice paper by Mafrogiannis in 2016 about the topic. We will rely more on Morse theory, or basically the conceptual ideas of representing a state space by representing or by computing critical points of a cost function on the state space, or in our case, critical paths on the state space. There are also a lot of publications on that. And our work basically uses Morse theory grouping applied to multiple robots. And I want to give you a very short overview about Morse theory, or basically about the conceptual ideas behind it. Basically, we say that a local minimum is an invariant of the cost functional under optimization. So let me just explain you how this works. So on the left picture, you can see a very small, very simple state space where we have a green start position in the lower left corner and a red goal configuration in the upper right corner. We have also a small obstacle in the middle in gray. And if you just sample paths, you would get maybe something which is in the second picture. And the core idea now is to associate a cost function to each of those paths and an optimization function which takes the path as input and which can locally minimize the cost function. And in the end, independently of which path you pick, you would hopefully always converge to a critical path, and we can then visualize those critical paths, which gives you an idea of how this state space actually. And as an optimizer, we use a very simple path length optimizer. But if you're familiar with the literature about optimization there are many, many really good papers out there. For example, Stomp, Jump, Prejot, Como, functional gradients, descent, optimization over Gaussian. Okay, let me just very briefly explain the algorithm itself. So as an input, we have a state space X, or even several state spaces, which are all abstractions of each other, plus start goal states, and the output is a tree of local minima. And I want to visualize this for a very simple example. So imagine that we have 2 disk robots. The first one is numbered 1, the other one is numbered 2. and each robot has to go from green start position to a red goal configuration, and all robots can only move along line segments. So the first robot can only move horizontally, while the other robot can only move vertically. And the state space, which I just showed you, is basically the state space of those two robots. And on the left, you can see if we analyze this state space, we might find two local minima here for our case. And those correspond actually to two situations which we have. The first situation is where the first disk goes first, and the other one is where the second disk goes first. So basically, you can use this algorithm to identify high-level options which you have for a particular problem. And in this case here, you have to make this high-level decision of which robot goes first. And of course, if you have more dimensions, more complicated robots, there are many more local minima, and we need a way to group them together, and we do that using multi-level abstractions, where we take local minima, we project them down into a lower dimensional space, and we group them there together. And this actually gives you at the end. I don't want to go too much into details about multi-level abstractions. Please have a look at the paper if you want to know more about that. I will go on and explain more conceptually how the algorithm works. So let's assume for now that we have a single state space X, we have start goal states, and the algorithm works that we have a while loop. While we are within some time budget, we grow a sparse roadmap on our state space, and we use a sparse roadmap algorithm, which has been adapted from this nice work by Dobson 2014. We then enumerate n paths from start to goal using depth first search on this roadmap. We then optimize all paths, which with our optimizer, we remove duplicates, and we finally add those paths to our local minima tree and will return this local minima. And this is really the basic algorithm to solve it. And the paper itself, it adds more details to this basic algorithm, namely how you can incorporate multi-level abstractions using a component-based framework, how you can actually interact with this algorithm by choosing local minima, and also how you can clean up the sparse roadmap before enumeration, because this is a very essential feature to make this whole algorithm run efficiently. We have 6 scenarios which we evaluated for the paper. I wanted to show you only 2 of them. The first one is a scenario where we have the Baxter robot with 2 arms, and we consider this as a multi-robot planning problem where we have 2 manipulator arms. And on the left, you see the start configuration of this problem. Basically, the left hand is on top of the right hand, and the goal is to reverse this order, so to put the left hand below the right hand. Our algorithm runs for 13 seconds, and it finds out that there are 2 local minima, one where you move the left hand in front and to the bottom, or where you move the left hand back and below the right hand. The second scenario is 2 mobile base manipulators, which are at a crossing. We reduce this problem by projecting the state space down onto the base of the robots. And you can see on the left picture that this is something which resembles really this whole 2-disk problem again, where we have to decide which disk goes first. Our algorithm finds this out in 0.57 seconds, that there are 2 local minima. We then can choose one of those local minima, and we can use it basically as a constraint to find local minima in the joint state space. And those local minima there are a bit difficult to interpret because they correspond to clockwise and counterclockwise orientations of the joints. So more information, of course, in the paper. And in conclusion, what I have shown you is that we can visualize local minima even in multi-robot planning problems, and we do that using a Minima tree. The whole approach is based on sparse roadmaps, on depth-first search, on path optimization, and on multi-level abstractions. There are 3 limitations, at least. One is, of course, that we use a sampling-based approach, so if there are narrow passages present, it's very difficult to find them. We did some additional research in that direction. There's a paper about section patterns, which you can look into. Second limitation is that we really use a predefined multi-level abstraction, and if you want to learn that or adapt that on the fly, I can really recommend you 2 papers, one by Ichter and one by Brandao. And finally, of course, we didn't really specify what would be a reasonable cost or optimizer, and this is really something which has to be done the code is written in C++. It is, of course, open source, and we use extensively open motion planning library. You can find that on GitHub, and the link for OMPL is, of course, here, ompl.kavrakilab.org. That was everything. Thank you for listening, and if you have any question, then please just follow the links in the. Bye-bye.